Hi guys, welcome to Unit 7. So we're going to start off, this is a review from Algebra 1. The first half of this unit, in theory, is review, but we all know how true that actually stuck in our brain from ninth grade. So we're going to go over it again. So this next unit starts off with sequences. So sequences, luckily, are just a list of numbers. Sequences are literally a list of numbers, and we're going to be looking at patterns. We're going to be looking at the patterns that we find in these numbers and how we can express those mathematically, those patterns. So state the pattern and fill in the missing terms. I'm going to let you do this on your own because you can. So hit pause, fill in those missing terms for me. What is the pattern in that sequence? Hopefully you actually paused the video and didn't just wait for me to start back up again. So I have 3, 7, 11. It looks like I keep adding 4 each time. So 15, yep, 19 plus 4. Plus 4, yes, it's a plus 4 pattern. So the pattern is add 4 to get the next term. Add 4 to get the next term. But we have to be more specific. We started at 3. So when we describe sequences, you got to tell me start at 3. So we define sequences to be functions. We don't really need to get too much into this, but the key thing is sequences are an ordered list of numbers. Later on in this unit, we're going to take our list of numbers and add them up. That's called a series, but that's the second half of this unit that we'll deal with later. So sequences is a list of numbers, and we're going to try to describe the pattern. So consider the sequence A sub n. This is A with a subscript n. And what this represents is the nth term. So if I have the first term, the second term, the third term, the fourth term, the nth term is somewhere out there. So here's the first term, the second term, the third term. I don't know where it is, but here's the nth term. That's what that A sub n, when I say the nth term, that's what I mean. Somewhere out there in the list, I'm in seat number n. Seat number 1, seat number 2, seat number 3. Over here is seat number n. So here's the sequence, 4, 8, 16, 32, 64. Okay, I think I see the pattern here. It looks like it's a times 2 pattern. It looks like I keep multiplying by 2. So find the following. This is A sub 1. But I don't want you to think of that. I want you to think of the first term. What's the first term in this sequence? 4. What is A sub 9? This is the ninth term. Who is the ninth term in the sequence? Well, I just have to count. 1, 2, 3, 4, 5, 6, 7. Who comes next in line? Well, good thing my calculator's right here. 256 times 2. That's 8. And then I'm going to do it again times 2. 1024. And those of you who played 2048 during my class, you should be really good at this example because you know your multiples of 2 really well from playing that game. Yes, I'm talking to you 8th period. So A sub 9 is 1024. So here I want to do the second term over the first term. The second term over the first term. 8 divided by 4 is 2. The third term over the second term. 16 over 8 is 2. That ratio is 2. 7 over 6. Well, 1, 2, 3, 4, 5, 6, 7. Seventh term over sixth term. Guess what? It's 2. So what the heck is this ratio here? Well, the answer is 2. Hopefully, if you're following the pattern, it better be 2. But why is it 2? So again, here's a 1, here's a 2. I'm going to go all the way out to A sub n. Here's the nth term. Well, who comes before that? Who comes before the nth term? A sub n minus 1, the nth minus 1 term. So what this is describing here is if I take any two terms next to each other and do second over first, fourth over third, fifth over fourth, if I do that ratio of the nth term over the guy before it, this is the guy before, the term before A sub n. That's what A sub n minus 1 is. That ratio always comes out to be 2. And this is called, in this sequence, this is called a common ratio. This sequence has a common ratio. which means we're going to call it a geometric sequence. Hopefully you realize that we've heard that word before. This is a geometric sequence because that common ratio exists. It has to deal with repeated multiplication. There's a lot of new vocab with sequences, even though it's stuff we've already done before. Geometric is repeatedly multiplying by 2. I have that common ratio here. So how do you describe this sequence? Well, you start at 4, a sub 1 equals 4, and you multiply by 2 to get the next term. That's how we describe the sequence. And we're going to describe it as a geometric sequence because it has that multiplicative pattern. That's a lot of red. I'm shocked I haven't changed colors yet. So let's do this all again, but with a different sequence. So how about we actually pause the video right now and you try exercise 2 on your own here. Here's a new sequence. See if you can figure this out for me. So looking at this sequence, let's see what's going on. I'm not multiplying. It looks like I'm adding 7 each time. Okay, so there's an add 7 pattern. So the pattern here is start at 4, and we add 7 to get the next term. A sub 1, 4. The ninth term, 1, 2, 3, 4, 5, 6, 7. We have to keep adding 7. 53 comes next, plus 7 gives me 60. So here I want to do second minus first. Second minus first, 7. Seventh minus sixth, 7. So notice if I take the nth term in this list and subtract away the nth minus 1 term, the guy before him, if I do this guy minus this guy, smiley face minus cloud, what do I end up getting? Well, if I take any 2 consecutive terms and find their difference, I get 7. So remember that a sub n is the nth term, a sub n minus 1 is the guy before him, which gives me 7. This is called the common difference. The common difference. Why? Because you subtract the 2 terms to see what you're adding. So this is an arithmetic sequence. I know it looks like arithmetic, but it's called arithmetic. It's an arithmetic sequence, and it has a common difference, the number you keep adding. The pattern that we keep adding is actually called the common difference. So these sequences can be graphed. These sequences can be graphed, and here's the rule. A sub n equals 2n plus 1. So if I want a sub 1, guess what number I'm plugging in? I plug in a 1. 2 times 1 plus 1 is 3. If I want a sub 2, I plug in a 2. A sub 3, plug in a 3. I want the first 5, a sub 4, a sub 5. If you trust me, that comes out to be 9 and 11. So graph these. Be careful when you graph these. Here's my first term. My first term is 3. My second term is 5. My third term is 7. Notice, that's not 7. 7 does not come after 3. 4 does. It looks like it's a linear function. It looks like this arithmetic sequence here. Why is it arithmetic? I keep adding 2. I add 2. Is a linear function. Do not connect the dots. No. We go from the first term to the second term. There's no one in the middle here. I cannot draw that line in there because there's nothing happening in the middle. We go from the first term to the second term. We just skip right over it. What's the 21st term? A sub 21. Well, we play everyone's favorite game. Plug it in. Oh, I'm going to miss that, guys. I'm going to miss when all of you yell answers back to me. But that's okay. We can still do it virtually. I'll just pretend like you all did it enthusiastically. So the 21st term in that list is 43. The beautiful thing about this rule here, this is called an explicit rule. And if I want the 21st term, you plug it in. That's just some more vocab we're going to be talking about later on. Same idea. Consider a sequence defined by the pattern such that the first term is 1. All right, A1 is 1. The first term is 1. And to get the next term, you double the previous one. So it looks like the pattern is a times 2 pattern. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So let's graph this sequence. 1, 2. 2, that's not, wow, ouch, I can count boxes. 1, 1, 2, 2, 3, 4, there we go. 4, 8, 6, 7, 8, and 5, 16, 8, 9, 10, 11, 12, 13, 14, 15, 16. Again, don't connect the dots. No connecting. We cannot connect those dots there. And notice it has that, I'm doing my dance moves right now. You can't see them. I should have my little webcam here, but I don't want to overload the recording software. It has that exponential function shape. It has that exponential function shape because it's a geometric sequence. Why is it geometric? Because there's repeated multiplication. I have a common ratio of 2. So arithmetic sequences are linear. Geometric sequences are exponential. What's the 10th term of this sequence? Well, I can't just plug in a 10 like here I wanted the 21st term, so I plugged in 21. For this one, we've got to work our way up. We've got to keep on doubling to get that next term. And again, my 2048 players, you guys are good to go right now. 512. 512 is the 10th term. This is a recursive rule where I describe the pattern. I don't give you an actual formula to plug into. I describe the pattern. Again, more words we're going to be looking at as we venture into this unit. So at this point, for each of the following sequences, describe the pattern if one exists. So I'll do the first one, and then I'll let you guys finish the rest as a little OYO. We can still do OYOs, virtual OYOs at this point. So it appears like plus 6, plus 6, plus 6. So I'm going to call it arithmetic. I'm going to call it an arithmetic sequence. I'm going to say start at 1. And to get the next term, add 6. That's what I want for all of these. Tell me what type of sequence it is, if it is one. Tell me the first term, where do I start, what's my home base, and what's the pattern. So at this point, pause the video, and then I'm going to go through and give you all these answers here, and you can compare them with mine. So sliding over here, this is an arithmetic sequence. We start at 2 and we add 10 to get the next term. Uh-oh, it's not happy. There we go. 2, 6, 18. This is a geometric sequence. This is geometric. Why? Because we keep multiplying by 3. So we start at 2 and we multiply by 3 to get the next term. 18, 9, 4.5. So this one's a little weird because it's decreasing, and a lot of you probably said divide by 2, which is fine, but we can't think about it in terms of division. We need to think of it as multiply by a half. If I'm dividing by 7, that's times 1/7. If I'm dividing by 10, that's times 1/10. So this is actually geometric. I did red twice. Redo. Divide by 2, cross it out, really make it times a half. Gotta make it look pretty for you at least. Geometric, start at 18 and multiply by 1/2 to get next term, to get the next term.
We got a galaxy pen for this one. This is the arithmetic sequence.
Miss the galaxy pen here. Arithmetic sequence. We start at 14 and we subtract 3 to get the next term. That looks awful, so I won't use that again. This next one is also arithmetic. I'll go boring and just use plain old black. This is arithmetic. We start at -8 and we add, well, what do I add each time? I'm adding 0.75 to get the next term. I'm seeing crazy decimals here. I'm definitely not adding the same thing, so let's do a ratio. Let's do 25.6 over 32. That's second over first. And then we're going to do third over second. 20.48 over 25.6. Remember, we can find that ratio to see what we multiply by. So I'm picking up my calculator here. That was 0.8. 20.48 divided by... Oh, this is awesome. So it is geometric, and we're starting at 32, and it has a common ratio of 0.8. So we multiply by 0.8, 8/10, to get the next term. That was a tough one. That was a tough one there. And finally, this last one here. That's +5 plus 10. So it's not arithmetic. But also there's no ratio. 9/4 doesn't equal 19/9. 9 over 4 is 2.25. And 19/9 is 2.1. Repeating. So it's not geometric, it's neither. This is a special type of sequence we're going to look at later on, not in this set of videos, but it's neither. It's not arithmetic, not geometric, it's just a different list of numbers. We've did number 6, so we can skip that for today. So hopefully you found these problems pretty straightforward. There's a couple tricks in here, but we're going to be looking at these list of numbers for the next few videos. So at this point, I'll see you in the next lesson.